Publishing, and I'll be your host this afternoon. Today's webinar will focus on continuous galvanizing and aims to provide engineers, designers, and architects with good insights into continuously galvanized material, its selection, capability, and corrosion resistance. The International Zinc Association experts speaking on this webinar will shed light on the corrosion protection provided by zinc and aluminium zinc coatings, how continuously galvanized sheeting is manufactured, where it should be used, and how to specify continuously galvanized material. Take note that the Q&A function has been enabled, so please post your questions into the Q&A box, which you'll find on the panel at the bottom of your screen. The panelists will attempt to answer all your questions during this webinar. If you miss anything during the presentations, don't worry, we're recording the webinar and we'll be sending you a copy of the recording afterwards. We are also streaming the webinar live to the Engineering News YouTube channel. Panelists will also be available for you to contact afterwards. So let's get started. I'd like to introduce our first guest, Simon Norton. Simon is a corrosion and failure investigation expert and manages the International Zinc Association in South Africa and Africa. Over to you, Simon.
Good afternoon. Thank you, Shannon. Good afternoon, everybody. I'm going to start this webinar on continuous galvanizing with a discussion on how coatings prevent corrosion of continuous galvanized sheet. And I'll be taking you through the various coatings that are commonly used on continuous galvanizing sheet and how they actually protect the underlying steel from corrosion. But first, just a brief introduction to what is continuous galvanizing. Unlike batch hot dip galvanizing, continuous galvanizing uses coils of sheet that are formulated or prepared by a steel mill and then continuous galvanizing mill. Martin van Leeuwen, the Director of Technology from the International Zinc Association, is going to talk in detail about this. But if you look at this diagram, just to start the process of familiarizing you with it, initially the coil of steel is cleaned. It's an alkaline solution is used to degrease it. It's brushed. It then goes through an annealing process, which softens it. It also is exposed to a nitrogen-hydrogen atmosphere to remove oxides. It then goes through the zinc bath. If you have a look where my red point, my red marker is, you'll see that's the zinc bath. That could be a bath of other materials, which I'll talk about later. After that, it goes through a process to adjust the surface finish to the choice of the customer. It then goes on, it could actually be coated with a paint, or it's put through a process to apply an anti-corrosion or passivation coating. But this is not what I'm going to be talking about. This is just to introduce you to the process. Martin's going to talk about that in detail. Before we actually talk about those processes, we need to compare what most people are familiar with, that is hot dip galvanizing. If you look at the green arrow, you'll see that a piece of steel section that's hot dip galvanized in a batch process, and say greater than 6 millimeters in section, will acquire essentially what we could say two parts. The first part would be the blue part, which is really pure zinc, and the light blue component will be the iron zinc alloys. And if you look at the top at the coating thickness, you can see that you could achieve a coating of up to 85 microns. However, if you go down to the red arrow and you look at continuously galvanized sheet, there you see that the entire coating, or virtually all of it, is pure zinc, and there's very little in the way of iron zinc alloy. If you look at the coating thickness, it's less than 20 microns. So when you're doing your designs, you have to be very, very careful how you select your continuous galvanized material, choose your application, and decide on where, and then have a look at where you're going to apply it. If you look at what is known as ISO standard 9223, there are various corrosion categories. And on the right-hand side, you'll see the rate at which zinc is consumed. So for argument's sake, if you're going to take a continuously galvanized sheet with 20 microns of coating, and you've got a facility that's very close to the sea, and you lose about 8 microns a year, then you're going to have less than 2 years life for your continuously galvanized sheet. However, if you are inland, let's say, and we're in South Africa now, in Johannesburg, and you're losing coating at the rate of 0.7 microns per annum, then you're going to get a very, very long life out of your sheet. So the rate of corrosion is important, the rate at which zinc corrodes, and you need to understand that you're not dealing with hot dip galvanized steel sections from a batch process, but continuously galvanized material. Now, at the root of all protection of corrosion of galvanizing is the galvanic series. This is a simplified version. It's normally recorded and measured in seawater at 25 degrees centigrade. And if you look on the table, you'll see that at the top, gold, silver, platinum's not in there, but platinum would fit in there. Stainless steel, 304, 18% chromium, 8% nickel. They are essentially noble materials, and they are far, far away from what are the very reactive materials, which we're going to talk about. If you look at the red arrow, you'll see that I'm going to be looking at zinc. And in relation to carbon steel or other alloyed steels, there's a big difference between the two. And essentially what you're getting is a galvanic cell. So the galvanic series underpins all of what we're going to be talking about with regard to the corrosion protection that zinc aluminium, and zinc aluminium and magnesium provide. But we'll come back to that in a minute. Zinc, atomic number 30, atomic mass 65.38. It has an inner shell structure of argon. It has an outer shell structure with a 4s level with 2 electrons. It's open to being easily oxidized from zinc 0 to zinc plus 2. And it sits in the part of the periodic table known as the transition metals. It is the heart of batch hot dip galvanizing, continuous galvanizing, and is a very important material in many other spheres in industry. And we're going to be initially talking about the application of zinc in continuous galvanized sheet. If you look at this microstructure, which I show you, you'll see that the underlying layer here, where my cursor is moving, is the steel. If you look at the scale, you'll see that it's a 10 micron scale in the electron microscope. And there you can see the micron measure. And if you look at that length, you can see that coating there, which is the galvanized zinc layer, is about 10 microns. A very thin iron, aluminium, zinc intermetallic layer forms, which is quite different from batch hot dip galvanized steel. And the coating you get there with multiple layers of iron zinc alloys. If you look at the top, you'll see what are referred to as spangle boundaries, and I'll come to that in a minute. This is how the cooling process happens when zinc crystallizes and solidifies in continuous hot dip galvanizing. And as you can see, we have a structure here that's known as a dendritic structure. Dendrites are similar to trees. You have a trunk of the tree. If you look at the blue arrow, you'll see there's a trunk of the tree and then the branches of the tree, hence the term dendritic structure. And the zinc solidifies down this blue axis and then outwards from there. This then provides you with the spangle or pattern, and you can choose when you purchase for your design whether you want no spangle or a very large spangle. Now, zinc performs 3 functions when it protects the underlying steel from corrosion. Firstly, if you look where my cursor is moving, it forms a barrier, a physical barrier to the atmosphere and to the polluting or corrosive environment. Secondly, it provides cathodic protection. As I showed you on the galvanic scale or the galvanic series, zinc is far more reactive than iron in steel. So zinc then goes and converts itself into a dissolved material, provides 2 electrons, which then are used at the cathode, which is on the other part of the zinc surface, or the iron zinc surface. And the third function is a passivation layer. But let's just go back a bit. Firstly, we've got the barrier. Secondly, here is a drop of water. You've now got a galvanic cell. You've got iron, which is part of the steel, and you've got zinc. And because you've now got water, you've got an electrolyte, There probably are other materials dissolved in the surface, chlorides or small amounts of dissolved materials. So you've got electrical conductivity inside this drop, and you've got all the ingredients for a galvanic cell, and the galvanic protection is provided by the zinc. The third part of it is the passivation of zinc. What happens is that the carbon dioxide in the atmosphere, the oxygen in the atmosphere participate in an electrochemical reaction, because at the end of it all, the protection of zinc is an electrochemical reaction, and I'll show you now. There you can see a particular steel surface, and it's got some continuously galvanized zinc on the surface. So imagine this is your continuously galvanized sheet. This provides barrier protection, a physical layer. Then you've got a drop of water. At this particular point, zinc converts and is oxidized to zinc plus 2 and provides 2 electrons, which flow through to this part of the surface. So all over the surface, you've got anodes and you've got cathodes. At the cathode, those electrons provide a reduction of oxygen to water. And that's the galvanic protection of steel that you see that zinc performs in galvanizing. If you look over here, this particular layer of zinc has provided partial galvanic protection. We sometimes refer to that as the throw. And finally, no galvanic protection over here. In some quite recent research, it was quite clearly shown that when zinc reacts with a marine atmosphere that's sheltered, these products are formed. I put it up for you for interest because this particular one, zinc carbonate hydroxide, is what forms a very hard layer and ultimately protects galvanized material. There is a software, a computer model, which looks at what is the interface between the zinc on the surface of the steel and the liquid gas interface. And if you can see over here, zinc oxide forms, then there are cathodes and anodes on the surface, and a variety of other compounds form. And then these are the materials that are in the atmosphere or in the environment to which zinc is exposed. If you look at corrosion products formed on a zinc sheet, continuously galvanized sheet, and it's in a sheltered ambient environment, initially oxygen and moisture form zinc oxide, zinc hydroxide. Then carbon dioxide forms zinc carbonate. If you've got an atmosphere with sulfur dioxide or sulfates, you get these compounds. If you've got a marine environment, you'll get these. And if you look underneath here, you'll see that these form within seconds, those within hours, these within days and weeks, and these within months and years. And this has a considerable influence over the painting and coating of galvanized materials. So we've just briefly run through the corrosion protection of zinc-coated, continuously galvanized sheet. And you'll often see terms like Z60, Z150, Z275. That relates to the weight or mass of zinc per square meter on the continuously galvanized coil, the photographs of which you can see here. Typically, this material could be used in automotive vehicles. In South Africa, Duferco Steel Processing in Saldanha produced this sort of material. Here you can see the numbering. There you can see the mass of zinc per square meter, and there's the nominal thickness. So it's vital to know what material you choose, and it's vital to know the nominal thickness and to know the rate of corrosion of zinc in the atmosphere where your cladding or your product is going to operate. You can also choose no spangle, minimize spangle, etc. ArcelorMittal in South Africa have moved a step further than that. What they've done is they've taken continuously galvanized sheet, Z200. So you can see there, Z200, 14 microns roughly of zinc. There, 14 microns of zinc. They put a pre-treatment on to ensure the primer stays on. They put a primer of 5 microns and a top coat of 20 microns. This is a decorative coat. So you can choose green, blue, yellow, according to their schedule on their brochure. This you would use inland. If you're going to operate near a marine environment, you would use this particular coating called Ultim, where there is a greater and a higher mass of zinc on the surface. So they're using Z275 and more organic coating, both inside on the one side and on the reverse side of the material. This is just typically what, and we're talking about corrosion, what ArcelorMittal will measure on their product and test in order to distinguish between Chromadex Standard and Chromadex Ultim. If you're going to design, you're advised to speak to somebody who can assist you with this, but you can actually see the performance of the material. Now, if you move away from just pure zinc and you add aluminium to the bath and a small amount of silicon, then you get what is termed alu-zinc, or trade name Galvalume, or trade name Zincalume. In South Africa, for those of you who are South African listeners and viewers, BlueScope, an Australian company, markets Colorbond, which is an it's Zincalume with coatings on it, and Safel, they market Color Plus. So we've spoken about zinc. Now we look at aluminium in the periodic table. Number 13, it's got 3 electrons in its outer shells, so it's open to ionization, aluminium plus 3. Again, we look at the galvanic series. There sits aluminium, not quite as reactive as zinc, but very close to it. So a combination of aluminium and zinc coated over or galvanized onto carbon steel sheet will allow for galvanic protection, barrier protection, and the formation of various oxides and corrosion products which protect the underlying steel. And this is how it's done. Aluminium is added, silicon comes together with zinc, and they form the aluminium zinc coating. The coating forms a very specific dendritic structure. In other words, branches, a branch off a large trunk. You can see the microstructure. I've shown it to you here. This is a cross-section of an aluminium zinc coating, and you can see there's the underlying steel, there's an aluminium-rich area, there's a zinc-rich area, and then there's small particles of silicon. The way this mechanism works from a corrosion protection point of view is that this zinc-rich area starts to corrode preferentially. And there's a big difference between the way in which a zinc coating corrodes on sheet in continuous galvanized material and the way alu-zinc does. In zinc, it's uniform removal. In this case, it's preferential. So the zinc forms various compounds and they preferentially corrode. The aluminium doesn't initially react. It only reacts later. So it forms an additional barrier. And consequently, this type of galvanized coating, alu-zinc, has a much better performance than just a pure zinc coating on continuously galvanized sheet. Here is an example of the South African manufacturer's Color Plus. This is an alu-zinc coating with an organic coating to give the color, and you can see it's a very attractive and long-lasting material. The way in which it's formulated is there's the zinc aluminium layer. So you've got zinc aluminium on steel, then there's a pre-treatment layer, a corrosion inhibiting primer, and the top coat. And you can choose the top coat. This client has chosen this color, you could choose something else. BlueScope, in their term, have their trademark product called Zincalume, and then they put a conversion coating, a universal inhibitive primer, and a finish coat. They also do the same on the inside. And they have various grades. They have ones for inland areas, which they call Clean Colorbond, and they have another one for the coast called Clean Colorbond Ultra. And if you wish for more details, we can give it to you. That's what it looks like. Really beautiful, and it provides a long-lasting. Certainly, you can, in the right environment, you can see this roof lasting for 25 years without a problem. Just to show you again, to remind you, aluminium, they're the aluminium-rich areas, they're the zinc-rich areas, and they're the silicon flakes in alu-zinc. Now, the second last coating I want to look at is when you add magnesium. It's an alkaline earth metal. It's got 2 electrons in its outer shell, oxidized to magnesium +2. And here is a magnesium aluminium zinc coating. Magnesium forms compounds with zinc. It forms compounds with silicon. You've got the same silicon flakes, the aluminium-rich areas, the zinc-rich areas, and this material has got even better performance than alu-zinc. Zincalume, marketed and trademarked by BlueScope, have moved from Zincalume to the next generation where they've put magnesium in. I won't go into the detail. I have explained that earlier on. And the South African manufacturer and European manufacturer ArcelorMittal also sells a product called Magnellus. It hasn't got an organic paint coating on it, but it's got the steel coating. There's the steel substrate. It's then got the Magnellus magnesium, aluminium, zinc as an alloy, which provides outstanding protection. And then you can either have what's called e-passivation or oiling on the surface. This just gives you an idea of there is a continuously galvanized zinc sheet, one with a specific alloy mix of zinc, aluminium, and magnesium, more of it, and the Magnellus layer, and the performance in how it survives this particular cyclic corrosion test. If you want more information on cyclic corrosion tests, we can speak afterwards, or you can email us. Finally, what is known as Galvan is also an outstanding material. This material consists of 95% zinc, 5% aluminium, and what are known as mish metals, in this case, rare earths, cerium and lanthanum. They have a very particular lamellar microstructure, and this material is very easily drawn and is used frequently on wire and other components. Galvan is available in South Africa components. This is what the microstructure looks like. Again, aluminium plays a role. However, the way in which this corrodes is quite different to alu-zinc, in that you've got two separate microstructures here, one of an aluminium-rich area, another a zinc-rich area. As a summary, here's a hot-dip galvanized coating, a zinc overlay with a small intermetallic layer on steel, a Galvan coating over here with lamellar, and an alu-zinc layer, which is the color bond, the color plus type of material I showed you from Safel and BlueScope. If you take a look at this with Galvan and you say, let's say we go to 8 years, you'll see that if you've got Galvan, the loss in corrosion due to corrosion is about 50 grams per square meter. If you go to look at just a general zinc galvanized sheet, you can see it's over 100. So by choosing Galvan, you can acquire an enormous improvement in corrosion performance and life of your structural design or build. Finally, to summarize on all the various forms of continuously galvanized types and coatings and their work in corrosion protection, we have galvanized material, which is almost all zinc with a small amount of aluminium. Then we have Galvalume or alu-zinc or zinc-alume, which is zinc, aluminium, and silicon. You have Galvan, which is zinc with 5% aluminium and a bit of cerium and lanthanum. And finally, there's something I haven't talked about, which is galvanneal, where after going through the continuous processing, the zinc galvanized sheet is put through another annealing furnace in order to induce diffusion of the iron from the steel sheet into the and provide a material that's very easily painted and has got quite a good performance. So there you are. There are all the means protecting steel from corrosion. And I hope that at least this has given you an introduction to what's available to you as designers and engineers. Thank you very much, and please send us any questions you might have. Thank you.
Thanks so much, Simon. Now we know what coatings are applied to continuously galvanized material and how they stop corrosion. But exactly how does continuously galvanized material get manufactured? To give us these answers, I'd like to introduce our guest speaker, Martin van Leeuwen. Martin is the Director for Technology and Market Development at the International Zinc Association and is based in Brussels, Belgium. Martin is a chemical engineer and has wide experience with continuously galvanized manufacturing plants. Over to you, Martin.
Thank you, Shannon. So good afternoon, everybody. Try to share my presentation. There we are. So I'm going to talk to you today about the manufacturing of continuous galvanized sheets. First, I will touch on the production, then I will talk a little bit about coating weight control, post-coating processes. I will also touch on the coating types and their finishes. There will be some overlap with the story of Simon. I have some to say about spangles in galvanized material, coating weight specifications, coating properties. I will mention some process and product standards, and I will finish with an overview of other good references. So galvanizing is a process for rust-proofing iron and steel by the application of coating. Three of the most used processes for applying zinc to iron and steel are hot dip galvanizing, electric galvanizing, and zinc spraying. Most galvanized products are coated using the continuous sheet hot dip process. It involves immersing a moving steel continuously sheet for 2 to 15 seconds in a bath of molten zinc, which is at a temperature close to 465 degrees C, to form a metallic bonded zinc or zinc iron alloy coating. This same hot dip immersion process is also used to produce other coatings such as zinc aluminum coatings. There are 4 main steps performed in sequence on modern hot dip coating lines: cleaning the steel strip, annealing or softening of the steel, coating it with zinc, and then treating or conditioning the surface. These consecutive processes are completed in a matter of 4 to 10 minutes, a feature that used to take 3 to 6 weeks before the advent of continuous galvanizing lines. The start of the line has an unwinding station to unwind cold rolled coils and to weld them end to end. The end of the line has a surface conditioning, inspection, oiling, and rewinding station, winding into galvanized coils. In a zinc pot, the moving strip passes around a rotating submerged zinc roll and is redirected vertically to exit the bath below the coating knives. Stabilizer rolls just under the surface of the zinc help control strip shape and vibration, allowing a stable, flat strip to pass between the knives. Typical gas knives employ a low-pressure, high-volume approach to deliver of the wiping medium. Pressure is the principal control parameter for coating mass control, although height, distance from the strip, and angle of the knives are also adjustable. Automatic coating weight controls using artificial intelligence technology have been installed on some lines to produce consistent, steady-state coating weight with a low standard deviation. Traditionally, air is used in the gas knives. Some lines use nitrogen gas, which allows low pressure wiping and results in a smooth, bright finish, superior coating weight control, minimum dross, and little, if any, coating sag. After the zinc has cooled, twin-head X-ray fluorescent gauge, utilizing a 2-inch focused beam, repeatedly scan across the width of the strip. The gauge provides a continuous readout of zinc thickness of both top and bottom surfaces for control purposes. After galvanizing, a range of post-coating processes can be applied. Skin pass milling or temper rolling is an important part of producing exposed quality sheets. 4-high roll design is common and incorporates tension bridle rolls before and after the temper mill to allow extensions up to 2% to achieve the required surface finish and mechanical properties. Work roll bending is incorporated for optimum shape control. A wet rolling practice prevents surface contamination and zinc hiccup. On most lines, load rather than extension usually control the temper mill. Then the tension leveler, located immediately after the skin pass mill, provides superior flatness while maintaining precise control of elongation. The presence of intermediate bridle rolls between the temper mill and leveler permits control of elongation independent of the temper mill load. Extensions of up to 1.5% are attainable with the leveler. For non-automotive end users, the next step in the CGL process is for the strip to be treated with a chrome bearing solution. This is to provide resistance of the formation of wet storage stain, a term traditionally used in the galvanizing industry to describe the white zinc corrosion product that sometimes forms on the galvanized steel surface during storage and transportation. Chrome solution cannot be applied to automotive end users because it interferes with phosphatability, paint adhesion, and weldability. Some suppliers have developed non-chrome bearing chemical treatments. They involve the use of phosphoric acid and a heavy metal other than chrome-6, which is toxic. The performance of these new treatments is slightly inferior to their chrome-bearing cousins in humidity and wet stack tests. The strip then passes through the inspection station, which can incorporate horizontal and vertical and/or top and bottom visual surface inspection. The area is equipped with both fluorescent and strobe lighting. Some lines have automatic inspection to assist human inspectors in assessing surface quality. An electrostatic oiling unit is used to apply a light, consistent, precisely controlled film of either a rust preventative oil or single-phase pre-loop both surfaces of the sheet. Immediately after oiling, the strip is recoiled on a mandrel to produce coils to the customer's order weight. The galvanizing process is called GI, and the coating is then called Z from zinc. If the zinc coating is left to freeze after the gas wiping operation, it forms a traditional GI coating or zinc coating, the thickness of which is a function of the action of the coating knives. GI has a bright metallic luster and is usually applied at coating weights of 100 grams per square meter and heavier. The galvanizing process is called GA. Coating is called ZF for zinc iron alloy. Reheating the strip to a temperature of 590 degrees C immediately after leaving the coating knives produced galvanizing. Immediately after leaving the coating knives, this produces galvanizing. The zinc is still liquid when the strip enters the galvanizing furnace, and the reheating restarts the zinc iron diffusion reaction and breaks down the inhibition layer that formed while the strip was in a zinc bath. Simon talked about this in his presentation. After 5 to 10 seconds, a dull gray matte coating is created, which has a bulk iron content of 9 to 12%. The surface is rougher than with galvanized and therefore better for paint adhesion. The galvan process is called GF. The coating is called ZA from zinc aluminium. This coating has a metallic luster and results from uninfluenced solidification of the zinc aluminium coating. Depending on the manufacturing conditions, crystals of different sizes and brightness develop. This does not affect the quality of the coating. Both the process and the coating are called ZM for zinc magnesium. The finish is obtained when the zinc magnesium coating is left to solidify unrestricted. The surface has a metallic appearance and may be matte to bright. Variations in appearance, such as a tendency to darkening, are possible. And then, last but not least, the galvalume process is called GL. The coating is called AZ from aluminium zinc. The products are delivered with a normal spangle. Normal spangle means a finish with a metallic luster, which is the result of unrestricted aluminium zinc crystal growth during normal solidification. If a pronounced spangle is desired, this shall be indicated especially at the time of inquiry and the order. A few more words about spangle in galvanized zinc coatings. As most GI lines today use lead-free spelter, the spangle size is smaller than 0.5 millimeter and difficult to see. But in the past, lead or antimony were added to the bath to produce large, flowery spangles. With the very small spangle produced by a lead-free bath, it is much easier to make an extra smooth product by temper passing, which, for example, is important for automotive. Many coating lines that agree to produce a visible spangle pattern do so today using only antimony additions. This meets with marketplace needs in a number of industries, especially those that use bare, painted galvanized sheets. These people still want a spangle pattern. The use of antimony mitigates the health concerns of lead. However, spangle boundary corrosion can remain an issue. Quality of the coating is not affected by spangle formation. Users often ask if there are specifications that govern the size of galvanized spangles. Unfortunately, there are no quantitative specifications that require this feature of galvanized sheet. Spangle size can be affected not only by the zinc chemistry and cooling rate, but also by other factors such as the smoothness of the substrate. Consistently controlling spangle formation to a specified size and then verifying compliance would be an extremely difficult task. For this reason, spangle size terminology is qualitative. It is defined as regular spangle, as minimized spangle, or as spangle-free. In the absence of specifications for galvanized sheet spangle size, these figures 2 to 5 shown in this sheet are suggested zinc size ratings provided by the Galvinfo Center. These tables provide an overview of the available coatings. The correct selection of the coating is the decisive factor for any additional processing and must be coordinated with the intended use. Due to the enhanced corrosion protection of ZM coatings, zinc magnesium coatings, the applied coating masses are typically lower than with regular Z or zinc coatings. ASTM A755 is the American standard for steel sheet metallic coated by the hot dip process and pre-painted by the coil coating process for exterior exposed building products. Section 4.1.6 on page 3 states that the recommended minimum coating mass for use in exterior exposed building applications is Z275. It goes on to say that exemptions to these minimum designations can be considered when the environmental conditions are of such low corrosive potential, such as, for example, a very dry climate. In these cases, a lower coating weight, for example, Z180, may be appropriate. EN 508 Part 1 is the European standard for roofing and cladding products from metal sheet. Table C1 on page 23 states that the recommended minimum coating mass for use in exterior exposed building applications is Z275 in Spain, 350 in other countries. This EN standard also specifies recommended minimum coating mass for steel sheet with organic coating, as well for both exterior and interior applications. I didn't mention that all on this slide, but these are available. So these various recommended coating thicknesses can be found in the standard itself. In principle, hot dip coated strip and sheet can be processed like cold rolled or electrolytically galvanized sheet. In practice, however, the specific characteristics of this material create essential aspects that must be taken into consideration for certain types of processing. For that reason, it is useful to indicate the type of forming and processing to the manufacturer. This table shows a general comparative assessment of the characteristics of hot dip coated steel products. It is clear from this overview that the corrosion behavior improves with the addition of alloying elements, such as aluminium and magnesium, to the coating, but the forming and joining properties are of particular importance to automotive applications where stamping and hot welding are widely used techniques. Galvalume coatings are not a good choice for automotive sheet. The suitability of the other coatings depend on the final use. Galvalume or ZF improved joining properties of ZF coatings are compromised by reduced forming properties caused by increased galling and stamping. This slide presents an overview of standards and specifications available for continuous galvanized sheet. A lot of important information is available in these standards, such as the minimum coating weights for various applications, amongst others. Other good information on the continuous galvanizing process and products can be found at the website www.galvinfo.com. It is a website of the Galvinfo Center, which is part of and paid by the International Zinc Association. Galvinfo Center organizes an annual production training course for galvanizing line operators and maintenance staff. In this two-day course, all operational process and equipment aspects of continuous galvanizing are presented. And more information on this course can be found at the website. This brings me to the end of my presentation, and you can find my details here if you have any more questions. Thank you. Over to you, Shannon.
Thank you very much, Martin. It's always interesting to learn about how galvanized material is manufactured. I, for one, found that very interesting. Thank you so much. I'd like to take a moment now to hear from our audience. I'm going to launch a poll. You should see it on your screen now. And it is a poll that focuses on your experience as engineers with choosing and using continuously galvanized material, whether it be zinc galvanized or LU zinc galvanized. So you can see the questions here. Do you specify continuously galvanized sheets in your professional work? Have you experienced failure or degradation or corrosion of roof sheeting in the past 3 years? Do you know the difference between LU zinc galvanized steel sheet and zinc galvanized steel sheet? Do you specify any particular type of fasteners for your continuously galvanized roof sheeting? And finally, which of the following continuously galvanized roof sheets do you specify? I've made that one a multiple choice just in case we've got viewers who specify a range of them. So I'll give you a few minutes to look at that. You can answer at your leisure. I'll give it a few more seconds. About a third of our viewers have voted now. Let's see if we can get any more. Right, I'm going to end this poll now. We've had about half of our viewers take part in this poll. Let me also share those results with you. So here we can see 67% of people do specify continuously galvanized sheets. An equal mixture of an experience of failure or degradation. Simon will be the person to speak to if you answered yes for that one. Also, all of you are more technical than I am, and you do know the difference between LU zinc galvanized steel sheets and zinc galvanized. It seems that many of you, more than half of you, do not specify a particular type of fastener. And 83% say that they specify ArcelorMittal Chromadeck Ultim. Right, thank you for taking part in that. We appreciate you participating. This feedback is very useful to our panelists in the zinc industry and the galvanizing business. Now that we know about the coating types on continuously galvanized sheet and how the sheet is manufactured, let's hear some expert advice on its application and use on roofing, cladding, and light metal framed structures. To tell us about these applications, I'd like to introduce Terry Smith. Terry is South Africa's leading expert on galvanizing and its application on steel structures and in construction. Terry, please go ahead. Terry, it seems you're on mute. There we go, we can hear you.
Okay. Okay. Sorry, I seem to have lost something.
We can see your screen, Terry.
Okay. Okay, I'm going to talk, good afternoon, ladies and gentlemen. I'm going to talk a little bit about starting off with the history of hot dip galvanized sheeting. Question, why does old galvanized sheeting in South Africa last longer? And I'm sure some of you have seen some of this. Prior to 1950, all sheeting in South Africa was batch hot dip galvanized and imported, already profiled from the UK. Here's an underside of a roof in George, fitted out in 1928. Coating thickness measured in 2015 as 45 microns after about 87 years. There's a house built in Tontelduis near Dahlstrom, shot at during the Boer War in 1899. Notice the rust only adjacent to the bullet holes. In 1873, Paul Kruger, who was the president of the Transvaal at that time, built a home on his farm, Buchenhuntfontein, and ordered profile batch galvanized sheeting from the UK. On arrival, he found that the sheeting would not cover the roof of the house. They made a bit of an underestimation. So the advantages of profile sheeting, he inspanned the oxen and wagon and flattened the sheeting, which now covered the roof. This produced the saying, a boer maak 'n plan, and in English, a farmer makes a plan. In 1994, we were told that the original sheeting was still in service. It's 121 years old. What is continuous hot dip galvanized sheeting? And you heard the same, very similar things from both Martin and from Simon, but I'm just going to go through it. That's the coil that you find is after galvanizing when it's rolled up. And this is the continuous process, a coil of sheet up to 1.85 meter, which is decoiled, welded end on end, and passed through a annealing furnace held at about 900 degrees C. Traveling at about 180 meters a minute, it passes through a bath of molten zinc held at about 450 degrees C. And as it exits the zinc bath, it travels through a series of gas or air knives which control the coating mass. Typical coating mass in accordance with those two standards, 4998, which is the structural grade of pre-gal, or 3575 for commercial grades. We look at typically the Z275, which is an individual coating thickness of about 235 grams per square meter, or the equivalent coating thickness nominally about 19, with a minimum of around about 13.2. And calculating the mass of coating thickness in continuous galvanized coatings, this is a typical example. Z275 is the mass of the coating in grams per square meter. The 2 is, then it's divided by 2, which is both sides of the sheeting, and the density of zinc, which is 7.13, gives you a coating thickness of around about 19 microns, and similarly with Z450. The minimum coating thickness, which is held in the small print, 40% of the individual value, which in terms of Z275 is 235, divided by or multiplied by 40%, divided by 7.13 gives you a minimum of 13.2 microns. How does hot dip galvanizing control corrosion? Once the zinc carbonate patina formed, which Simon talked about extensively, that's a bit the reaction between the galvanized sheeting and the moisture and carbon dioxide in the atmosphere. The hot dip galvanizing provides a predictable, slowly corroding barrier. And in terms of the environment, there's a number of specifications or standards, the ISO 14713 Part 1 and the ISO 9223, as well as the ISO 12944, have these corrosion categories. And we're looking at, say, C3 atmosphere, which is probably largely 90% of this country. The corrosion rate of zinc is about 0.5 to 2 microns per year. So the applicable life would be in excess of about 10, 15 years. The C5 environment, corrosion rate is about 4 to 8 microns a year, and a Z275 sheeting would last about 3 to 5 years. Here we look at an example of that, atmospheric corrosion in Cape Peninsula, South Africa. You're looking at the map here. If you look at the southeasterly winds, which blow in over high wave action and over flatlands of Mitchell's Plain, very corrosive conditions up to about 8.5 microns per year, and up to 3.5 kilometers away from the high water mark. Here we have two sites, which is Simonstown and Gordons Bay, and you can see purely by the landforms, the corrosion rate is a lot less as a C3 atmosphere. And here we have a particular site, Capricorn Park, which I'd like to show you an example of the incorrect material. choice bias specifiers. The word galvanized can incorporate a number of different coatings with vastly different performances. Therefore, the choice of metallic zinc coating should be selected according to the corrosivity of the site, coating thickness, and relevant standards should be referred to in the project specification. Yeah, you see an underside, eaves of the underside of the building, and on that side is hot dip galvanized by general practice, and the residual coating 161 microns. You can see the chloride layer on the surface. In the background, you can see a zinc electroplated bolt is certainly corroding. And here you have the purlins, which are commonly made often from a Z275, which has only got a residual coating of about 5 microns in other areas where the red rust is attaining. And that's after 3 years of exposure. Very important to consider those things. Again, how does it protect? Metallic zinc coating provides cathodic protection at damaged areas or cut edges. How it works is the Galvanax series, which Simon mentioned, and here you can see a corrosion cell where the zinc acts as the anode, the steel the cathode, with an electrolyte and electrical connection. The zinc corrodes preferentially to the steel when you have those 4 things in place. Zinc is anodic to steel, so deep scratches up to 3 millimeters wide and less, and at cut edges, zinc will sacrifice in preference to the steel. And here you can see some continuous galvanized sheeting that's been used on top of a fence after a number of years of exposure. The effectiveness of the cathodic protection is dependent on the zinc content and the coating thickness. So corrosion creep is impossible. White rust or wet storage stain. When freshly galvanized steel is stored with moisture trapped between the contacting surfaces and access to free-flowing air is restricted, wet storage stain or zinc hydroxide might form. White rust will appear as a surface stain, whereas wet storage stain is a voluminous, white, non-protective corrosion product. Should damp conditions continue, zinc corrosion will continue. Removing the cause will stop further formation. And the surface treatment mentioned by Martin, the sheet manufacturers pacify the surface or oil it to prevent, generally prevent the white rust or wet storage stain. So store the galvanized sheeting in correct positions on site, limit it to the exposure to rainfall, particularly when it's closely packed, and also allow air circulation to move between the profile when stored on site for a longer period of time. I think ArcelorMittal talked about at least 2 weeks. If you're going to do that longer than 2 weeks, you need to separate it. Here you can see some light white staining, superficial staining on the surface of sheeting, and here's some wet storage stain which has compromised the coating because of its failure. Removing the wet storage stain or white rust, use a stiff bristle, not wire brush, or a wet Scotch-Brite cleaning pad. If necessary, add a cleaning solution such as 5% ammonia or acidified sodium dichromate, a 5% sodium dichromate plus 0.1% sulfuric acid. And then don't forget to thoroughly rinse with a potable running water thereafter. Pier sheeting and fixings, typical different profiles. All these need screws and fasteners to put them down. And years ago, different fasteners with different coating thicknesses were exposed in environments where they failed. And SAN 1273 was introduced, which has different corrosion rate formulas for different types of coating thicknesses on bolts, reminiscing to the actual coating thickness on the sheeting. And so you shouldn't have this type of failure anymore, where the actual screw is actually had an effect on the sheeting. Then you get concealed fixed sheetings, which allows all the fixings to be underneath the sheeting, so the corrosion of the fasteners and the brackets is far less. Here we have some applications of sheeting. different applications, which is very seen over the years. When the use of inferior products, which happened several years ago, became rife with price dominating over performance and durability, concerned industry players formed the South African Metal Cladding and Roofing Association in an attempt to restore credibility. So for more information, you can contact Samancra at that information. There's a case history of a gutter in the greenhouses in Abu Dhabi. I was asked to go and have a look because South African manufacturer had supplied these gutters and they started failing within a short period of time. The competitive export pricing, which the manufacturer was obviously faced with, so he sent the cheapest, most easier one, assuming that the desert was benign. These greenhouses, the gutter forms an integral structural role, and failure of the gutter will actually have a result of failure of the greenhouse. The facts: the aggressive surrounding sands, extensive winds, and light rainfall of about 5 millimeters per year resulted in under-deposit corrosion failure of the gutter and obviously structural failure of the greenhouse. And yeah, you can see some typical pictures of the gutters from the underside, and obviously the stretched fabric had failed after that. Here's the inside of the gutter. You can see it very well corroded with that under-deposit corrosion because the sand got in there and it was moist for quite some time afterwards, and it corroded the zinc away. The bottom side was still 30-odd microns, and these were all Z450. So solution: understand the site and specify correctly. In this instance, consider thicker steel gutters, general hot dip galvanizing of the gutters, and plus added protection of appropriate paint systems, greater slope of the gutters, shorter distance between the downpipes, and regular removal of the debris and maintenance of the gutter. Applications: motor vehicles. In the 1970s and the 80s, vehicles took on this form, and I'm sure everyone that was driving a vehicle those days had the experience of rust, particularly along the joints of one's vehicle. In order to enter the car market, the Japanese and Korean car manufacturers gave a 6-year warranty on corrosion. And in 1987, all vehicles sold into the USA had to have a 10-year corrosion warranty. Substrate primer coating changed from organic zinc to metallic zinc. Started with zinc electroplated sheeting, but this process consumed too much power, and they changed to different manufacturers. In 1999, car manufacturers in the USA and IZA formed the Galvanized Auto Body Partnership, which is called GAP. And there you can see it's quite an organization. Today, there's at least 80% of the vehicle manufacturers used metallic zinc substrates. And here you can see, particularly in America, from the early 80s, where it was 10% and now 80% in the early 90s. Free zinc or galvanneal coatings are today the most common, and corrosion warranties are now common up to about 12 years. Light metal frame buildings, houses, industrial buildings, etc. Again, light steel frame buildings started in South Africa in 2007. It's a cost-effective alternative building technology. It offers speed of construction, accuracy, excellent thermal properties, logistical cost advantages, and design flexibility. For more information on this, you can contact SAFSA at that same email address that you had before. Applications for storage tanks, etc., which is a very big use in South Africa. Make sure that the supporting frames are similarly protected from premature corrosion. And finally, applications: razor wire. Note that razor wire, in most instances, for security fences is generally made from a Z100, galvanized sheet, which is about 5 microns, and thinly coated wire. So when these are used in moderate to aggressive environments, it's the first part of the fence to fail. And as you can see, this is a galvanized fence, hot dip galvanized fence with razor wire on the top. And here's another one, which is also after about a couple of years in an aggressive environment. You can see the razor blades actually have disappeared. So in order to embellish the continuous galvanized razor wire blades, one can always paint them in appropriate paints, or supply it with a alternative material like stainless steel, or even consider batch hot dip galvanizing the coils, which we've done in a couple of instances. It's rather expensive, but it is a solution to look at. Thank you very much.
Thank you very much, Terry. A reminder to our audience that the Q&A function is enabled, so please be sure to send us any questions you'd like our panelists to answer at the end of the presentation. I'm going to now share with you an informative video on the continuous galvanizing process.
The new continuous hot dip galvanizing system has been designed by SMS ZMAG so as to produce high strip qualities on the one hand, and on the other to be utilized in a versatile manner for a wide product mix. In spite of being 60 meters high and over 300 meters in length, it is still a compact plant for a hot dip galvanizing line. It comprises the following: entry group with 2 payoff reels, welding machine, entry accumulator, cleaning section, annealing furnace, zinc pot with air knives, induction furnace for galvannealed grades, cooling zone, and strip accumulator. Skin pass mill, tension leveler, roll coater for post-treatment, and exit accumulator. Trimming shear, inspection section, oiling machine, separating shear, and finally 2 tension reels. The system will contain up to 3 kilometers of strip between the entry and exit groups. The welding machine joins it to form an endless strip. After the entry accumulator, the X-Pro strip cleaning section appears. First of all, spray cleaning is performed here with an alkaline solution. Then the strip is brushed. The electrolytic cleaning section. Renewed brushing and rinsing with hot water, with drying to finish. This multi-stage cleaning process removes not only very fine iron particles, but also emulsion residues. The strip runs through the entire process chain uninterruptedly at up to 180 meters per minute. The strip accumulators act as buffers. The annealing process gives the full hard cold strip a soft microstructure at up to 850 degrees Celsius. At the same time, the surface texture becomes altered so as to allow improved wetting in the zinc bath. The zinc pot with the flanged-on heating inductors. Controlled by process models, the strip is guided through the 460-degree zinc bath. Uniform coating is ensured by the air knives with scan skew technology. In this, the knife sets itself automatically to the center of the strip. If the strip is in an inclined position, the knife follows accordingly and is thus always parallel to the strip surface. This means that the excess zinc can be blown off precisely with air or nitrogen. For those strips with galvanized coatings, a downstream induction furnace is waiting, which can be integrated optionally into the process. The strip can be heated quickly to 530 to 550 degrees Celsius by the induction furnace. The galvanized layer is formed by the diffusion of iron in the zinc coating. These strips possess a harder surface, are easier to weld, and can also be painted more easily. Returning to the line. Here, in the multi-stage cooling zone, the strip first cools down to below 300 degrees Celsius. In the water quench process, it then drops to around 40 degrees Celsius. The strip accumulator, the skin pass mill. Here, the material property and the surface texture desired by the customer are set by means of a rolling process. In most cases, the galvanized strip is provided with a defined degree of roughness for better painting properties. The last areas of unevenness remaining in the strip are eliminated by the tension leveler. Now that the surface of the strip has been annealed, galvanized, skin passed, and made flat, the next process is to protect it. In the roll coater, either a passivation is performed or an anti-fingerprint coating applied by means of a pickup or applicator roll. The trimming shear follows. Designed as a double-headed shear with a quick change system for precise setting of the market width. The inspection stand, where the strip is assessed in horizontal and vertical directions for any possible surface defects. The oiler. Here, the high-quality strip surfaces are given a preserving protective coating, comprising rust-preventing oil or deep-drawing oil, or a combination of the two. The flying crank shear cuts the strip and, at the same time, is used for sample taking. Finally, strip winding takes place gently, step controlled by one of the two tension reels. A complex process chain thus comes to an end.
Some interesting information there. I hope you all enjoyed watching that video. We can move now to the Q&A. We can see what questions we've got from our audience. I see some of them have already been answered by some of our panelists. So what I would like to ask is, perhaps Simon, you can answer this one. What is the difference between Z60 galvanized sheet and Z275? And which would you recommend at the coast, specifically in South Africa?
the person to really answer that question is Terry Smith. Terry, unmute yourself and tell us.
Yeah, thanks, Shannon. Thank you, Simon. Z275 ideally should not be used at the coast anyway, even though it's got a minimum coating thickness of about 13 microns. Z60, which unfortunately is coming into our country from countries like China and India, has a coating thickness minimum of about 2.8 microns. So using that down on the False Bay coast where the corrosion rate is 8.5 microns, you're looking at about 2 to 3 months of life before it's actually starting to corrode. So it makes a huge difference in its use. And unless it was subsequently painted with some organic coating system, which is appropriate to the use that it actually gives you. But it's a very thin coating.
Thank you, Terry. I would also like to know, what is Chromadeck and what is clean color bond, and are they suitable for use as roof sheeting? Is that also a Terry answer, or is that for Simon to answer?
I'll take that one up. Can you just repeat the question again, please, Shannon? I just want to get that quite clear.
Certainly. What is Chromadeck and what is clean color bond? Are they suitable for use as roof sheeting?
Both are suitable. They are trademarked, branded names. Chromadeck is supplied by the South African manufacturer ArcelorMittal. It's an international company, but we've got a major plant in South Africa. They've got two types, Chromadeck and Chromadeck Ultim. Ultim would be used near the coast. Chromadeck standard would be used inland. And Color Bond is a product which is actually known as Clean Color Bond. And there are a variety of products that's supplied by the Australian company BlueScope. Some of it's manufactured in Malaysia, some of it's manufactured in Australia. It's an outstanding product, as is Chromadeck. And the Colorbond product also has Colorbond Ultra, which you would use if you're in a marine or a corrosive environment. Both are suitable for cladding and roofing.
Thanks very much, Simon. I think we'll take one more question, and the one I would like to ask is, when using continuously galvanized coated sheet for roofing, that's zinc or alu-zinc, what is the other key factor to consider in specifying material, such as specific fasteners that should be considered?
Well, that's a Terry Smith question. Terry Smith knows that one very well.
Thank you, Simon. Look, the other considerations, obviously there is a specification or a standard that's been put together by the Institute of Steel Construction under Samancra, which obviously determines whether you use what material below another material. For instance, a sheet into a gutter, or a gutter onto another sheeting. I believe that standard is currently with the SABS. That's something to consider. But I've forgotten your question now, Shannon.
If there's any specific fasteners or any specific material that should be specified, such as specific fasteners for roof sheeting.
Yeah, certainly the fasteners that have been graded according to the corrosivity of the site is important, because obviously having a fastener which has adequate coating equal to the coating thickness or corrosivity of the sheeting itself makes sense. So the whole thing corrodes at the same rate, which makes total sense. Where in the past, the fasteners often used to be used with just electroplated fasteners bought off the shelf at the various building outlets, and didn't have enough coating thickness to achieve the actual end.
Thanks very much, Terry. I think that's all we've got time for today. So I'd just like to say thank you to everyone who participated in our live Q&A. If we didn't get a chance to answer your question, or you didn't get a chance to ask it, please do be in touch with us afterwards, and we will happily connect with you after the webinar. I'd just like to find out if our panelists have any last parting words before we say goodbye.
I've got a last parting word. I'd like to, on behalf of the IZA in Africa and our operations in Africa, thank Terry Smith for participating in this webinar and preparing thoroughly. I'd also like to thank Martin van Leeuwen, who directs and is now directing research and marketing from Brussels for the IZA across the world, to thank him for participating and for preparing for this. And I'd also like to thank Cream Media for their forming the second webinar from IZA. We hope to have further ones. I also want to remind the listeners that there is a copy of Essentials of Galvanizing available either electronically or in a print version for your library, and we've got plenty of copies for your colleagues. So if you give us your physical address, we'll send you by courier multiple copies of the Essentials of Galvanizing. And finally, to those who are as participants who've attended this, thank you very much. If you've got any questions, please give us a call. Thanks, Shannon. Thanks very much.
Thank you also very much to our panelists, Simon Norton and Martin van Leeuwen from the International Zinc Association, and Terry Smith of TSA for joining us today. And of course, we thank our attendees for taking the time to log in and learn about continuous galvanizing. If you would like more information, please be sure to visit the International Zinc Association's website at www.zinc.org. The recording of today's webinar will be sent to you in due course, and if you have any additional questions, please do be in touch. You can reach us at shannon@creamermedia.co.za. Thank you so very much. Stay safe, stay well, and goodbye.